All right, welcome to Step 24 Notes. We're starting Unit 5, which is about exponential functions. We're going to learn how to graph exponential functions. So you need to grab your calculator. You need to have your calculator with you. I won't be able to display mine side by side in this video, so have your calculator near. We're going to graph the exponential functions and identify their key characteristics, and then we're going to solve word problems relating to exponential growth and decay. So what is an exponential function? What makes an equation exponential is when x, the variable, is in the exponent. So the variable is in the exponent. The base, b, the base of the exponent is a number. And this is the number that determines growth or decay. If b is bigger than 1, the equation will show exponential growth. And if the base is between 0 and 1, so between 0 and 1, so it's a decimal or a fraction between 0 and 1, this exponential equation will show decay. A is another number multiplied by b raised to the x power. A is the starting value. It's the y-intercept. We know that the y-intercept is where x equals 0. So if we sub x equals 0 into this equation, we get a times b raised to the 0 power, and anything raised to the 0 power is equal to 1. So a times 1 is equal to a. So the y-intercept is always x equals 0, and when x equals 0 in this equation, a is the y-intercept. So we have to be careful here not to multiply a and b together before we raise b to the exponent of 0. Remember order of operations, and exponents are before multiplication. So let's look at these examples of exponential functions. Y equals 2 times 3 to the x power. We know this is exponential because x is up in the exponent. So a would equal 2, b is equal to 3, the base of the exponent. And if b is greater than 1, we know that this is going to show growth. 3 is greater than 1, therefore this equation is going to show growth. If we look at the next equation, we have 4 to the x power. We know it's exponential because x is in the exponent. The base is 4. So again, it's going to show growth. A is invisible, and the only time A we have multiplication and the number is invisible, that means A must equal 1. If we look at y equals 1/2 to the x power, this time the base of the exponent is 1/2. 1/2 is between 0 and 1, so this one's going to show decay. And again, A appears to be invisible, therefore it must be 1. Let's talk a little more about the base. So it's the base of the exponent that determines whether the function is going to grow or decay. This number, the base, it's a rate. It's a percent. And we can think about this percent as either growing or decaying. So if we have 24%, something can grow by 24% or something can decline by 24%. Well, its growth factor, if it's going to grow by 24%, means that we're going to have 124% come back, because we're going to have 100% of what it was and then 24% more. So the growth factor, 124%, factor for 24%. Well, if we're going to decline by 24%, 100 minus 24 is 76. So therefore, we're only going to bring back 76%. 76 as a decimal is 0.76. So we're comparing the percent to 100. We're always comparing to 100%. And then we're converting them to a decimal. The growth factor, the base, will always be in a decimal. In decimal form. We do not add, subtract, multiply, or divide with percents. The numbers that are in the equation are always going to be the decimal equivalent. So let's continue here. If we have 98%, we're going to grow by 98%. That means we're going to nearly double. So we're going to bring that back the 100% of what was and bring back 98% more. The decay factor, if we're going to decline by 98%, then we only have 2% coming back. The growth factor would be 105%. In decimal form, it's 1.05. The decay factor, if you're going to decline by 5%, then you have 95% coming back each time. All right, let's go ahead and graph, state the y-intercept, domain, range, growth or decay, and finally the equation of the horizontal asymptote. So in your calculator, go to y equals, clear anything out, type in 2 raised to the x power, and hit zoom 6 to graph. Now I'm not going to spend a ton of time graphing these exponential equations. I can see that this is leveling off at 0. Looks like it's going through the y-intercept at 1. I'm going to verify that by looking at the table to see if there's any easy points to graph, and over 0 up 1 is the first one. That is in fact the y-intercept. Over 1 up 2, over 2 up 4, 3, 8, and that'll do it. Classic exponential, it's going to grow up really fast. Okay, we've graphed the y-intercept, over 0, up 1. The domain, is negative infinity to positive infinity. It's always negative infinity to positive infinity for the 3 functions we've learned so far this year: linear, quadratic, and exponential. The domain is negative infinity to positive infinity. We could sub any x value into this equation we wanted, and we would get an answer back. There's no issue with subbing in x values. The range is a little more restricted. Knowing that this is leveling off, and it's never going into the 3rd or 4th quadrant. It's never going below the x-axis. So none of the negative y values exist. We can sub in any x value we want, and we're always going to get a positive number back. So our range goes from 0 off to infinity. This graph is clearly showing growth. It's increasing fast as we read the graph left to right, confirmed with b is equal to 2. The base of the exponent is equal to 2, which is greater than 1. Therefore, the equation should show growth. In the equation of the horizontal asymptote is the invisible horizontal line that the graph is never going to touch nor cross. And the equations of horizontal lines are y equals, and it's going through the y-axis at 0. The equation of this line is y equals 0. The horizontal asymptote is y equals 0. The 0 from the range and the equation of the asymptote will always be the same number. This equation is declining. The y-intercept is 0, 1. The domain, for all exponentials, is negative infinity to positive infinity. The range again is 0 to infinity. It's leveling off at the x-axis. So the horizontal asymptote equation is also y equals 0. And this graph shows decay. Okay, this fourth one, we can see that it's pushed up off the x-axis 2 units. And it's no coincidence that this plus 2 is what moved the whole function up 2 units. So the range doesn't go from 0 to infinity, because from 0, 1, up to 2, there's no graph at these y values. So the range, the y values start at 2 and go up to infinity. The horizontal line that the graph doesn't touch or cross is at y equals 2. Given the following exponential function, identify whether the change represents growth or decay. Okay, well, we know that it's exponential because x is in the exponent. If I want to know whether it represents growth or decay, I have to look at the base of the exponent. So I have to look at this value. 0.943. This is between 0 and 1. Therefore, those three signs stand for. Therefore, this represents exponential decay. Then part 2 of this says determine the percentage rate of increase or decrease. It's the same value, the base, it's going to tell us this information. It's the rate of increase or decrease. Well, it's decay, so we should show decrease. We have a decrease of how much? Well, only 0.943 or 94.3% is returning as x grows. So to find the difference, we take 1 minus that. And we get 0.057. So we have a 5.7% multiplied by 100 to get the percent. So we have a 5.7% decrease. Let's try another one like that. Given the following exponential equation, identify the change represents growth or decay, and determine the percentage rate of increase or decrease. So we're looking at the same value, the base of the exponent, 1.08. Is greater than 1. So this equation is going to show exponential growth. Since it's growing, we'll have an increase of what amount? Well, comparing this to 1, okay, we're going to compare this number to 1. This number is greater than 1 by how much? The 0.08, so there's an 8% increase. The base of the exponent, the determinant growth and decay, and the percent increase or decrease. The rate of increase, which is the rate of growth, or the rate of decrease, which is the rate of decay. Determine whether the set of data shown displays exponential behavior. Write yes or no, explain why or why not. Alright, so before we start, let's talk about what will show exponential behavior. Well, the x's, first of all, just need to increase or decrease by a constant amount, by a constant number. And if that happens, then we look at the y's. The y's, if they also increase or decrease by the same amount, so we're adding or subtracting same number to get from y to y, well then this is an exponential. If we're adding or subtracting the same number, this is linear. If we get from y to y by multiplying or dividing by the same number, this is exponential. So we check the x's first, and then we check the y's. So to get from x to x, it looks like we are adding 1. So good there. To get from y to y, we are adding 3. So this is not exponential. In fact, it's linear. X is 0, 5, 10, 15. So we're adding 5. Looking at the y. Not subtracting 10. It looks like we're dividing by 2 or multiplying by 1/2. Either way, yes, that makes it exponential. To determine if it's growth or decay, you have to look at what it's multiplied by. So the equivalent dividing by 2 is multiplied by 1/2. 1/2 is between 0 and 1, so this is going to show decay. Or you can look at the numbers and they are decreasing. X's looks like we're adding 4 each time, and the Y's are doubling. So this is exponential. And it's growing. The y's are increasing. X's are changing by subtracting 20 each time, and the y's are changing by subtracting 20 each time. So this is not exponential. All right, a couple more. Miss Kempler told her English class that each week students tend to forget 1/6 of the vocabulary words. Forget 1/6 of the vocabulary words they learned the previous week. Suppose a student learns 60 words. The number of words remembered can be described by the function. The number of words remembered can be described by this function. So starting with 60, each week they remember 5 out of 6. They're forgetting 1/6. X is the number of weeks that pass. How many words will the student remember after 3 weeks? So X equals 3 weeks. So W of 3 is equal to 60 times 5/6 raised to the 3rd power. Type this into your calculator. Exactly like that. Use the parentheses around the fraction. So after 3 weeks, the student will remember approximately 35 words. A new car is purchased for $16,200. The value of the car depreciates at 14.25% per year. What will the value of the car be to the nearest cent after 6 years? Okay, so this time we're going to have to write the equation. So this is the base of the equation. So let's fill in what we know. A is the initial value. Well, the new car is purchased for $16,200. So $16,200 is the A value. The percent is going to help determine the B value, but it's not that easy. We don't ever sub the percent in to an equation. So we need to find the B value. If it's depreciating at 14.25%, well, 100 minus that 14.25 is 85.75%. So if it's depreciating at 14.25% each year, that means it's keeping the value of